Okay, one more example here. We're going to look at calculating the pH, but we're going to work all the way from just having the mass of the salt and the volume of the water to having the pH. So we have 1 gram of sodium fluoride. Our first step here is we have to find concentration. To do that, we're first going to convert to moles. Sodium fluoride is 23 grams per mole plus 19 grams per mole. So I got 1 over 42 here. 0.0238 moles. And so I need the concentration of that, which will be the moles over the volume. Remember here that we need our volume in liters because we want molarity. So 0.2 liters. And I get a concentration of 0.119. Okay, now sodium fluoride is going to dissolve to form sodium plus and fluorine minus. Sodium is the conjugate of sodium hydroxide, which is a strong process, which means it's not going to do the reverse reaction, and so we can neglect it. F minus is the conjugate of HF, which is a weak process, which means the reverse reaction is significant. So F minus plus H2O is going to form HF, acting as a base, taking the hydrogen and leaving behind hydroxide. I have an initial concentration of F minus to be 0.119, and I'm going to assume I have no HF and no OH in my solution. I need my K for this conjugate base process. I can find that as long as I know the equilibrium constant value for the original weak acid process using this equation. Hydrofluoric acid, I think, is going to be 6.6. 6.6 times 10 to the negative 4. So, solving for Kb, or the conjugate, I messed that up, hold on. I got 1.52 times 10 to the negative 11. So with that in hand, I can anticipate my change and come up with my equilibrium values. The equilibrium is going to shift this way because I have zeros. That's going down, everything's 1 to 1. And I'm going to be able to use my 100 rule here because the concentration of my reactants is going to be much bigger than this Kb value. So what do I got here? Like 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.8 times 10 to the 9. Doesn't matter, it's much bigger than 100. So this is almost certainly going to be a good approximation to say that x is small. And so this is approximately to 0.119. I will check that at the end on the way by, but it's going to be good in this case. So now writing my Kb expression for the conjugate reaction. So I can use 0.119 down here instead of 0.119 minus x because x is small enough, and my value for my k is 1.52 times 10 to the negative 11. So x is going to work out to be here 1.34 times 10 to the negative 6. So this x, first of all, is way smaller than 0.119, so this is a good approximation. I don't have to go back and resubstitute there. But it also represents my hydroxide population. So I can find my pOH for this solution, and then use my relationship between pH and pOH to come up with the pH. So I got negative 5.87 or 5.87 here. And so I can recognize that my pH plus my pOH has to add to 14. So if I have a pOH of 5.87, my pH must be 8.13. Again, a pH that is pretty close to neutral water, representing the fact that this is the conjugate of a weak acid, but this conjugate is very weak itself. The acid HF isn't that weak, so then its conjugate process is pretty weak, leading to a very small hydroxide population here. But it is, still substantially bigger than what we'd find in neutral water, and so this is acting as a base, creating more hydroxide than we expect it to be there otherwise. So that's how you can get the pH of a basic salt.